So hello there, today I'm going to show you how I made this scene. I'm going to be focusing on the lightning setup and the splash flip simulation, the water simulation that is driven by the endpoint of the lightning here. And just to preface, a large bulk of the flip simulation, I used a tutorial by Hernan Llano. I think that's how you say that. And he has a really great tutorial series on flip simulations here, on this flip simulation in particular, where he goes over how to create a custom surface tension setup, how to fill holes, and I think going through this tutorial series will help you understand how to build a setup like this better. So I went through this, thought it's really great. I'll link it in the description below. In my tutorial, I will go over the settings and the setup, but I won't be explaining everything in detail of how the flip simulation works, or at least not as detailed as the tutorial that Hernan did. So let's get started. As you can see here, the scene is pretty simple. I have the can, I have the lightning bolt, I have the splash, the flip simulation, a floor, a background, a camera, and 3 lights. For the can, I just imported it, added some materials, scaled it down with a match size, scale to fit, and set that to the size you can see right here. This is really important, so the flip simulation is really scale sensitive, so this size worked out well for me. If you want a different look, you can experiment with the size as well to see what suits your project best. I then dropped on an out null so I can source it, use this as the collision for my flip simulation, and then I have a subdivision node to add some extra resolution for rendering. So for the lightning bolt, I started off with the idea that I wanted to have an area around the can where the lightning should strike. So I created a circle and inserted it with a poly extrude node, so I get this area where points are going to be scattered. And I did the same for the top. And so at the top and the bottom, on each frame, there's going to be 1 point that is randomly scattered. Or not on each frame, I did it on every 10th frame. So as you can see here, that's the basis of the whole lightning setup. And of course, you can define where the start and end point should be. So if you move this around, you can also have the lightning strike somewhere else quite easily, or rotate this. So you can really art direct this, or you can even animate these areas or add extra areas here if you want lightning strikes here. So we start off with a circle. I then use a poly extrude node and set the inset to this value so I get this shape here around the can. Then I drop down a scatter node, set the force total count to 1. And then I have this expression right here that generates a new seed every 10th frame. So if you click on this, you can see you can switch between the output and the expression. And if I scroll through here, then on frame 9 we have 0, and then from 10 we have 1, and on frame 20 we have 2, and on frame 30 we have 3. And this is the bottom part. And for the top part, I have exactly the same thing, just at a different scale. And then I drop down another scatter node. I then copy the previously set seed value here. So right click, copy parameter, and here I right click, paste relative reference, and then I added a random seed number. So plus any number you want. And then you basically get the same function, but the seed is just offsetted by that number that is added. So it is on a different position. I then merge those 2 points together, and then I add an add node, set it to polygons by group, all points, and then these 2 points get connected. I then resample that, so I have more resolution to play with for the noise. And I add a curve view attribute, which creates an attribute from 0 to 1 along the curve. I then group this whole segment here and call this main. So I just drop down a group, set the group name to main, and then enable the base group, which selects everything. I then add some noise to this with an attribute VOP, and the noise is scaled at the end and the beginning. And this was important for me, so I can really control where it starts and where it ends, because if I wouldn't do that, as you can see here, let's just template the starting point or the end point here. So this is the endpoint, and if I don't scale it with the curve view attribute, this is that, then it will not connect with the endpoint. And I really wanted the splash to emit from the point where the lightning strikes. So I wanted this to match. And to do this in the attribute VOP, I just added, so to the position, I just added some turbulent noise. So this is the basis. I offsetted the turbulent noise with time, so I get an animation. And then I added a multiply and promoted this parameter here. So if you just middle mouse click on this one, you can promote parameter, and then you have a multiplier, so this can scale the time, which makes it slower or faster. If you set the value at the top, so here I have the speed value. If you click on this, you can rename it here to speed. And then I multiply the turbulent noise with the curve view attribute that is ramped. So I get a bind, get the bind node, type in curve view, and then connect that to a ramp parameter, node, and then set this to spline instead of RGB color, and then connect this up as so. And if you jump back up, you need to recreate this ramp here, so this matches up. So this part here that splits off is for the secondary bolts. I use a delete node with percentage value, so a very high percentage value is deleted. So drop down the delete node, set that to delete selected, select points, go to random, and then you can select a percentage value. And in this case, I fitted time attribute to the random function, which basically outputs a random value between 0 and 1 on each frame, or each time increment in this case. So it also takes into account subframes. If you're doing simulations, this is quite useful. So this 0 to 1 value, this random 0 to 1 value is then fitted with a fit01 function to 95 and 99. So I get a random value between 99 and 95 on each frame, as you can see here. And these points are then used to scatter the lightning bolts around. So on each frame, I get a slightly different amount. I use the p-scale attribute to scale the secondary bolts in size along the curve. And for this, I just use the curve view attribute, which we have. So we have that value from 0 to 1, and then we just remap that to p-scale. So drop down a bind, type in curve view, ramp that with a spline ramp, and then we have a multiplier again like before. So we can control the entire length of all of these separately and then export that with a bind export. For the rotation, I drop down a polyframe node, set the tangent name to n for normals, and then I drop down an attribute adjust vector, set that to n for normals, adjust value, direction, and length, set the operation to add, adjust with random, set min-max to -1 and 1, and if I enable the normals here, you can see on the polyframe node we get those nice tangential vectors in the direction of the curve, and with the attribute adjust we just add a little bit more random values in that direction, and that turned out to look really nice for this setup. So this is what we end up with. After that, I resample those lines, so we get an even distribution of points for the noise to work its magic. Again, I export a QView attribute, but this time I named it curveview2. So I have a different attribute to the main one, and then I group those secondary bolts again and call that sec. So I drop down a group node, set the base group to enable, set that to sec. After merging the secondary bolts in the main bolt, I added the same attribute VOP as before, so you can just copy this setup, paste it down here, and the only thing I added here was to add an add node, promote this parameter so I can add a random value to the offset, just to offset the noise, so it's not exactly the same as before. And then I have a color animation, so if I drop down the time shift node, so I don't have any animation, so I can show you this. I use the curve U attribute to drive on the color animation. I just use the curve U attribute. This ramp just travels up the lightning bolt. For this, I just imported the curve U attribute. I fitted the value to 0 to 10 in this case. And then I use the ramp node to repeat this 0 to 1 value. So this basically just creates what you can see here. It just takes a value from 0 to 1 and repeats it. If you increase the frequency, and you can set the blur here, so there are some settings there. And I really like this. And then I use the multiply with the time again, like before, to offset this, so it just travels up the lightning bolt. And this gives me this really nice effect. So up here I have this value from the multiply, from the time, to increase or decrease the speed of this animation. So if I reduce this, we can really see what's going on, and it looks pretty cool. So let's remove the time shift here. So this is what we have so far. And then I have an attribute wrangle to control the width that we're going to get with the polywire later on. For this, I basically wanted one width attribute for the main bolt and then a second width attribute for the secondary bolts, which are, so the secondary width is scaled by the width of the main bolt. So for this, I created a float value called main width first and set that equals to a channel ramp called width main. And I used the curve U attribute, which is the curve U attribute from the main bolt. And then I create a second float value called sec width in this case, but it really doesn't matter but how you call them. Just name them something that is easily recognizable. Here the same thing, just call it width sec. And then I use the curve U2 attribute. And then I export this, and then I export these values to float value, in this case f at width. And then I set that equal to main width. Do the same thing for f at width 2. In this case, I use the secondary width float value, and then I multiply that with the main width value. And if I just copy this up here so we can see the width, turn this off, we can see that I can separately now control the remap of the width attribute, which is really nice. The secondary bolts are not bigger than the main bolt. So if I don't have this multiplier from the main width, these get too big, and this doesn't really match up with this multiplier. It looks perfect. This is the lightning we have. So we get this. But as you can see, we don't really have that interval of when the lightning strikes. So this is where this comes in. Basically just have a null that is connected to a switch node. So this switch node switches between an empty and the lightning bolt. So as you can see here, we get this really nice striking effect. And then I have a second switch node where I basically just hand animate the value so I can turn it off at the end. And for this switch node, I have a couple of modulo expressions that drive this. We don't need this here. So if you shift click on this expression here, you get the animation view and you can see what happens. So we get a value of 0 or 1, and on each 20th frame, it gives me a value of 1 for 3 frames. So as you can see here, there's 1, 1, 1, and then it goes back to 0. And the next 20th frame, so from 20 to 40, we get another value of 1 for 3 frames. On frame 5, I always get a 1 for 1 frame. So this is what this does. This is the expression. Just type it in. And then again, I have the second switch node, which is basically just a hand animated value from 0 to 1, where I decide where to have that activated. So I have it activated here at the beginning, and then at the end, there's nothing. I then have the polywire after this all happens. Could also put the polywire at the beginning, but I think computationally it makes more sense to have it at the end here. And then I have a polywire. So I have a polywire for the main lightning bolt. I use the main group here, and then I have a polywire for the secondary lightning group, which I define here. And I use the scale attribute width 2 and the scale attribute width to scale the wire radius. So if you choose your wire radius here, your base, and then instead of constant, just choose attribute and type in your scale attribute, or just use the drop down here, you can control the width of the polywire. And then I split this off. I just have main width attribute, scale this up a little bit bigger. So this lightning bolt is driving the redshift light here. So if you drop down a redshift light with the light type set to area and change the area shape to mesh, you can just select your out node from here. So you just copy this, go here, paste it. This gives me basically the ability to have a cleaner light source that has a greater area than the lightning bolt, since I want the lightning bolt to be quite thin, but if you have a thin lightning bolt, then the light impact or the lightning strength is not as high. If you have more area, the lightning is more intense. So this is what I do for this. And I use this for rendering. So if you view this and then hold down Control and click on this, this will be set to render all the time. So you can just view everything, but this will always render. After having the lightning done, we select the switch nodes, go to action, create reference copy, and then copy those, paste them here, make sure that's set up right. So you have the bottom point synced up with the appearance of the lightning. So we always have that. So that's synced up properly, as you can see here. And then we can jump over to the splash, where we will source that point here. For a brief overview, we basically use this point to scatter or to copy to points a circle. Then we create some velocities that look like this. So it's outwards splashing fluids with this velocity. We create a source, which are just some points from a volume. We create a source for the velocity. So these velocities we created here will be copied over to these points. So we have a larger starting area for the velocity. So more of the fluid that is spawned here will be affected by that velocity. And then we have a bound object that creates a bound that we can use for the simulation. So we have a procedurally changing bounding box for the simulation to take place in, which is really nice. So you don't really have to take care of that manually and see where that goes. So the strength of the velocity drives the size of this with an offset. As you can see here, we have the bounds a bit bigger than that. And then, of course, we have the can as a collision object here. Let's get started with this setup. So as before, we start off with this base point that we import from the lightning. We add some random p-scale value that is determined by the time. So I take the time, put that into a random expression, which gives me a value from 0 to 1, and then I fit that with a fit 0, 1 with these values here. So this is how that is done. So if you create these float attributes, set the channel float parameter here. If you type this in, click this, and then these will be created. And then you can control the scale of the circle that is copied over here with these values here. So the maximum and the minimum scale that is created on each frame have smaller and larger circles. And if you want way larger circles, just increase the max value or the min value accordingly. So here I realized those, I use the max value to actually be the min value, but it honestly really doesn't matter because it's just a value from the highest to the lowest, and I switch these out. So this should be flipped. If you want to be accurate about this, this should be flipped. So the max value should, of course, be higher and the min value should be lower. So this should be the other way around. But the end result is the same. So in this case, it doesn't matter too much. Yeah, we start off with a circle. I add a mountain node, which is basically an attribute noise on P, on the position. And I deselect the Y component so we don't get any noise in that direction. So if you don't have that deselected, you get noise in the Y direction as well. And if we deselect that, we get this. It's just added, zero centered with an amplitude of 0.2. Played around with the element size till I got something that looked just slightly displaced. I didn't want a huge displacement here. I then resample this and create a curve view attribute. So I have a little bit more resolution on that circle. I had to reverse the normals here. The copy to points node just copies that circle on those points that spawn in. For the velocity shaping, as I mentioned at the beginning, the tutorial that is linked below goes into way more detail. So I'm not going to explain everything in extreme detail here, but I will go over how this setup works. So first, a couple attributes are initialized. So firstly, a normal attribute is initialized, and then we have the tangent v that is initialized here as well with the y component of 1. So it points upwards first, and then we set an integer value called numPoints to the current total amount of points. So endpoints 0 says the current input is taken, and then this will export the total number of points. You can check this by typing in I@test to create a test attribute, test integer attribute, and set that to equal numPoints. And then if you have your geometry spreadsheet open, you can see that the test value is 123. If you middle mouse click on this node, you will see we have 123 points. So that is correct. What this section does is basically create a tangent vector. So what a polyframe node would also do, select this, is create tangent vectors if it's set to bitangent. So this creates a vector between 2 points, basically, between 2 neighboring points, and then it will create this outward pointing vector based on the position of the point before. The only problem with the polyframe node is that it creates this weird vector at the end because it is based on next point, basically, this vector. So if we have the last point, there is no next point to get a vector from. So we get this one point, which is where the vector is off. And this code block basically does this. So it creates an if-else statement and says if the current point number is not the last point number, which this does, numPoints minus 1 is the total number of points. So 123 minus 1 is 122. And since Houdini starts counting at 0, we need to do this to get the last point number. And then it basically creates this tangent v vector normally by just using the current point position and the next point position here to create a vector that is then normalized. But so on the last point, instead of adding, it minuses that. So we get a fixed tangent v vector here. So this is basically what that does. And then this tangent v vector is then used as a rotational axis to create vectors that are pointing upwards. So this creates an empty rotational matrix. Eigen function does that. And then we have a float angle that is converted to radians, which is set here. So if you create a channel float, click that, you get this angle to play with, and you hit edit parameter interface. Go to your newly created angle. In this case, you could also go with less. So if I preview this, in this case, we export it as the normal. So this is what we're getting from this code section here. So we can do this. And I think it would be fine to just set it from 90 to 0 in this case. So on the angle, instead of minus 90, I think 0 is fine for what we're doing here, because I think this is all we need. And as you can see here, this is exported as a normal. And this normal is the basis of the velocities that we're going to use to splash out the flip simulation. So here you can control at what angle the flip is going to be splashed out. And here, lastly, if you middle mouse click, you can always click on the attributes to visualize them. So in this case, I want to visualize the velocity attribute, which is the attribute we will export last to drive the simulation. And in our attribute VOP, we basically take these outward pointing normals that we created. So if I just deselect this, so here, these normals that we created before are basically multiplied with the curve u attribute. So this value from 0 to 1 that goes around the curve. We use a ramp that looks like this. So if I preview that, oops. So if I preview this, you can really see what's going on here. So this ramp that I created before, this one here, as you can see, this shape we have repeated with this ramp node. So if you increase the frequency here, we get this really nice starburst shape, which then creates the tendrils. So this is the basis of this nice splash effect. And here I had a value of 25.3. So you get a curve view, a bind node with a curve view attribute. You drop down a ramp. Here you create this shape with a ramp. And then you use the ramp node with a higher frequency to repeat this shape along the curve. And that is then multiplied with the normal vector coming in that we had before. So this value here, this outward pointing normals, are then multiplied by that curvy shape. And here this multiply value is basically just a multiplier to increase or decrease the incoming vector. So if I go up, the initial multiplier here is just a control to how large those incoming normal vectors are. And then to add some extra noise to this, what we have here with this repeating shape, I use an anti-alias noise, get the position, plug that in here, and then I can promote these attributes here. So I can control the frequency, the offset, and the amplitude and the roughness to really shape how that looks. And I used a ramp, second ramp node set to spline, call this ramp 2 so it doesn't override this. And with this node, you can really, I need to activate this. And with this, you can really shape how your noise is going to be. So I played around with this ramp and the noise and the frequency and the amplitude to finally, just going back a bit, to finally get a shape like this. So I played around a little bit with this ramp to remap the noise. And you can play around with the frequency, the amplitude, and the roughness to get velocities that you like. And this is a representation of the splash, basically, how it's going to end up, since you're shaping the velocities that then generate the splash, or that get pumped into the flip simulation that then make up the splash at the end. So I would play around with these values and see what you like. So yeah, this is the whole setup. Again, just gonna make it a little bit bigger so you can see what's going on. So we have the curve view attribute, which is repeating with a ramp, that is multiplied with some noise, that is also remapped with a ramp, and then multiply that with the incoming normals, have a general multiplier for the incoming normals, and then finally I have a final multiplier so I can show, so I can control the total strength of those shaped velocities. And a really nice way of previewing those velocities, which you can use, is to just grab those, the velocity that we just created, so v at v, and then use a length function to export the total value of that velocity that we have. So this uses basically the strength of that velocity vector is used to then write out a p-scale attribute. And then we can use a copy to points node and a line to then, if I just deselect this, to represent the strength of the velocities and the shape. So here you have a geometry preview of the velocities, which is really nice if you just want to view this. And then after having built this, you can just play around with all your settings and really dial it in. And a second benefit to doing it like this is using the bounds node, as said before, to generate the domain in which this is going to be rendered. So after having shaped your velocities, it's time to prep them for the simulation. We drop down a point replicate, set that to sphere and scale that down. And here you can really see what that's doing. So it's basically taking in the incoming points, so the points that we have here, and then scattering points around those points. And I set the quantity to 100, so I have a relatively dense field of points where I then use an attribute transfer to transfer those velocities. So if you preview those again, you can now see we get these velocities that we created earlier, just to make sure that it's correctly transferred, we attribute transfer, because the point replicate can export attributes as well, but just to be sure, we just override this with the attribute transfer node, set that to points, and here choose the velocity attribute. And then finally, I have an attribute wrangle. So after having transferred the velocity attributes to these points, I then have another attribute wrangle. First of all, multiply the velocities again. And then I have a function which basically randomly on each frame generates a random value which is fitted again between a value of 1 and 4. So I get different velocity strengths on each frame. To do this, I created a float value max and then a float value min. And then I used a random expression driven by time. So this creates, again, a value between 0 and 1, a random value each frame. And then that is fitted with the fit01 function to the min value and the max value here. So if you wanted to have way larger values, you could just set the max to like 80, for example, and then you would get really large splashes. But for me, I just wanted to create slight differences between the frames. So a value from 1 to 4 was perfect, but if you want to have larger discrepancies between the splashes, then just increase the max value or decrease the min value. Just play around with this, see how this looks. But the visualization here is a good representation of how high the splashes will be in the end. So after you have done all this, this is the velocities done. And the next step is to actually create a source for the flip simulation. So for the actual fluid that is going to be driven by those velocities. So we start off with our circle here, and then we poly extrude that. And in this case, I just outputted the front, not the back, because I can use a subdivision node and this smooths out the top. And if I would have had the output back enabled as well, then we would get this shape, but I really wanted a flat floor. And then I polyfill this so we have a closed shape. And then I use a points from volume node where the point separation is driven. If you click on this, it's driven by the particle step from the flip object in our simulation. So I just copy this at the end and just paste this in. So it's always the same value as the one I chose in the simulation. And then I have a jitter scale set to 1 and a jitter seed set to $f. So each frame I'll get a different seed, just to make sure it's always a little bit different. And here, if you would want, you could set a viscosity value. In this case, I turned it off, but if you want to have a splash that has more viscosity, that looks like honey, for example, or oil, you could enable this here. So this is the source in the end, which is basically just some particles. And finally, before we can drop down the topnet, I imported with an object merge the can as a collision object, so I can just source it from here. And now it's time to dive into the topnet. And after you have set all this up and have these out nodes, so we need an out source for a fluid source, we need our velocities and our bound object. We can connect these to a topnet, just like so, dive in. After having all this set up, you can finally drop down the topnet. And in here, we have our ground plane, the static object, which is the collision can with everything set on default except the uniform divisions, which are a little bit higher. So we have a little bit of a higher resolution on the can, but we don't need that much. We merge that, put that in a static solver and merge that with this. Have a normal gravity node, flip solver, flip object. On the flipped object, we define the particle separation. So there's the resolution. Everything else is set to default. The input type should be set to surface sub, and this should be empty. So there shouldn't be anything in here. If something's in here, like by default this is in here, just delete this, because we won't be sourcing our particles from the flip object. We will be using the volume source node to use these particles that we created before. So you just copy this, go in here and then paste that here. And then we're gonna source flip. So you click initialize, source flip, and then you go to particles and click source particles. And by default, it selects the group particles. And if you delete this, it will just use all the points. So we didn't create any groups, so just delete this group, and that's all you need to do. So this is a really awesome way to continuously source fluids into a flip sim. So you can just create particles all you want, and these will be continuously, each frame be sourced in. This node does all that if set up like said. So this geometry VOP is where all the magic happens, where the velocities are sourced in and added into the simulation. On the geometry VOP itself, on inputs, you have to go to the input 2 and select second input, second context geometry. And this makes it so that this is being sourced from here. So if we dive right in here, we use a PC Open, which is a point cloud searcher basically. So it takes a certain number of points and a cone angle to search for points. And then we use a PC filter sec to the V velocity channel, set that to vector channel, select that. So it basically takes and connect this up. So we take the second input, put that into files, and then these two nodes basically search for points in a certain radius, which are defined here. So I have promoted the radius here. So middle mouse click on here, promote parameter, and then at the top you can select the search radius. In this case, I use the particle step, so the resolution of the flip object, divided by that by a number. And for this, it's a little bit tricky because you kind of have to play around with this number, but I realized that using the particle step number and then just increasing or decreasing that based on that number tended to result in something that was usable. So I would play around with the search radius if you're not getting good results and just see what works. So you just need to run the simulation and then change the search radius. This is very crucial. So it takes those velocity attributes that we created before, those outward pointing ones, and we multiply that with the time increment that is multiplied by the frame rate. So this bit tries to make sure that even when we change substeps, this does not break. I found that this is not super reliable. So this is based on the tutorial I mentioned at the beginning, but I kept it in there because it kind of worked if I played around with search radius here. So not too sure about the functionality of this. For my setup, it worked. And then we add this whole thing back to the velocities. And again, I would play around with the search radius. And finally, on this multiplier, we just basically control how much of those velocities are added in again. So here you have that velocity scale value, which we promoted from here, where we can control how much of those velocities are coming in. And this really is the heart of the system. And then I, again, have a pop drag just to add some drag to the flip simulation. I thought it looked good for my scene here. And on the flip solver, everything is pretty basic on the substeps section. So this is all default. On the particle motion, the really important thing is have receding on. Play around with surface oversampling. So surface oversampling basically fills in the holes that get created when the splash gets ripped apart. So if those holes get created, increasing the surface oversampling certainly helps. And another thing what really helps to create a very consistent looking simulation is the separation settings. So increasing the separation iteration, which basically makes sure that all these points have the same distance to each other, which creates a much more stable looking result. So increasing this really helped me. And this is the separation rate. So at what time rate will this separation iteration be applied? Playing around with these two settings can help to create a good looking splash. And then on the volume motion tab, the most important thing is setting the velocity transfer here to apic swirly, because for small scale fluid simulation, this is really important. And finally, on the volume limits, we source the input from this bounding box that we have here. So we're taking the size from this bounding box that procedurally gets created based on our velocity size. These are the expressions that you need for that. So for the box size, we take the B box, op input path from the current one and the second input, or in this case, the third input, but Houdini starts counting at 0. So 0, 1, 2. These are the ones that you want. So I would just stop, type these in exactly as they're written out here, to get the exact centroids and the exact B-box. And this just makes sure that we always have a nice size. And if you want to increase the volume limits, so the area in which the flip simulation is being simulated, just increase the bounding box at the top. So if you just copy all this, then you can go up here, change the bounding box padding, and you can create a little bit more room for the simulation, or less room, whatever you need. And the final setting I added here is the surface tension, which is set to 1. By default is set to 10. And I decreased this because the surface tension is very sensitive to depending on the size of the simulation. So if you have a larger simulation, you would need larger surface tension values. And if you have a smaller simulation, then you would need smaller values here. And here you can set the blur radius of that. And if you would want to have viscosities and you have the viscosity attribute enabled here, so this is enabled and has a value, then you can source that by just enabling the viscosity here and then enabling the viscosity pair attribute. But I'm not using this for the simulation. That's about it for the simulation. So now I just drop down a DOP import field node. I select my DOPNet, so I just drag this over here, or just copy and paste. And then I just select the flip object in the DOPNet. So I just select this, the flip object, paste it here. And if you paste it, you'll get an absolute path. But if you hit this, this will pop up and you can select export relative path, click accept, and you'll get this. After you have defined this, you just click the flip fluid preset, just click that and it'll create all this. So nothing you need to do there. And then I drop down a fluid compress node, just wire it up as so, and make sure that particle separation here. So you copy that parameter and paste it here. So it's linked up. So this value has to be the same as before, or it should be, to create accurate fluids in the end. And this is what I cache out. So the fluid compress node creates or compresses down the fluid simulation and gets rid of unnecessary attributes that we don't need for the surfacing. Just cache this out. And then the particle fluid surface node also has the particle separation linked up. Here you could either convert it to a surface polygons or to particles. So if you want to preview your simulation, it's quicker to just view particles. So you can also play that back way quicker and you can create flipbooks with that. And for final rendering, the only thing you need to do then, so for rendering, just select surface polygons and cache that out. And then you're ready to go. For the surfacing, you can play around with the adaptivity if you need a little bit resolution overall. If you want to do displacements, for example, then I would decrease the adaptivity to 0, so you get a very dense mesh. But the default value is quite good for fluids, because on areas where there's no detail, it will try to reduce the amount of geometry. But for areas where there's a lot of detail, we have more geometry, and that works out fine for rendering. And you can also play around with the filter settings here. And then just cache this out. If you're using the new file cache node, you can unselect simulation, and then it will try to use all your cores and export multiple frames at once, because we already have the simulation cached out. So here simulation has to be on. And here you can deselect that, so you can use all your cores and export multiple frames, cache out multiple frames at once, which makes surfacing quicker. So if you have a lot of threads, a lot of processing power, then deselecting that will really increase the speed of surfacing. And that's it. So after we have created the lightning and the splash and we have the can imported, it's time to put the scene together, do some lighting and some materials, but everything is pretty basic. The floor just has a basic iron material where I reduce the roughness a little bit, and it's just a grid. And then for the background, I just put a grid here, left a little bit of space between the floor and the background. I pointed a light upwards with a blue color. So I have an area light that is scaled like this. To get this sharper gradient, I just turn down the spread of the light. So the spread is turned down very low here. If I change this, for example, and make the spread a little bit broader, we get a nicer fall off, so you would have to increase the intensity, but I really like this effect I got here. Rendering with bokeh, so I'm rendering with depth of field on, and then this line here gets blurred very nicely where the floor is. So this looks looked pretty nice to me and got this nice effect. And then I have a second light, which is just pointing downwards on the can here. So I get a nice highlight here at the top and just some general light for the can. So if I turn this off, this would be completely dark. So you could also animate this and it would also look quite cool. Finally, for the lightning mentioned before, I have an area light where the lightning is referenced, and that's it. So if you want this file and you don't want to go through this whole tutorial, or you just want to get the file to get a starting point to create something different, just go to the description and you can grab the file on my Patreon or on my Gumroad. And if any support is welcome, so I can create more of these, because it's quite fun to share the learnings I get with people, and this would really enable me to do more. So if you're interested, just check out the description. If not, that's also cool. Just glad to share this with the world and see what anybody does with this.